Okay, welcome back for another lecture. This will be number 2 in the series for Physics 1. So now that we have an idea about what units we're going to be using and how to be put into SI units and convert from one unit to another, we can go on to the next bit, which is going to be motion. So we have motion here in one dimension. It's the easiest motion we can show in physics for starting is just one-dimensional, something in straight lines. And motion's important because it's one of the first things we do. They give it the term kinematic. Kinematic motion derives from cinema, like moving pictures, like a movie. So we'll be dealing with things that are moving in this one. So first we better get some terms in order like we usually do. I guess we better know where we started and where we're going to go would be the first term. So where did you come from? Where did you go? We're going to call that a position. Okay. So right now we're just going to call it X for right now. And it's the location of whatever your object is. They call it a particle. They call it an object. It can be anything as long as it is something with mass, and it's the location of that particle with respect to some chosen reference point. All right, so they might have different systems later on where we choose to look at rotational coordinate systems or straight line rotational coordinate systems. But that all comes later. For now, it's your position. It's where you are at. Okay. No matter how you look at it, it's where you are at, is your position in space. Okay? Now, a couple of things can happen with your position because we can change it. Okay? If you decide to take a step to your left or a step to your right, you have changed your position. And there's a couple of different terms that we use to describe that. One is known as a displacement. So the displacement would be the overall change in your position. And when I say overall change, that's what this triangular symbol here for is known as a delta. You can think of that as change of. Okay, so change of x. X right now is what we are considering position, so this would be the change in our position. And it's always equal to, so triple equal sign, always equal to, wherever you end, okay, which would be your XF. This F stands for final. It's your final position minus XI, I of course being your initial position. So where you ended up minus where you began, okay? And you can kind of see it over here as well. If we have a map through the woods, you're following a trail, something like that. It might be curvy, it winds around, it goes, it doubles back on itself, all that kind of fun stuff. The displacement, though, would be where you started, okay, the front of the trail, and where you ended, where you're currently at on the trail, and it would be the difference between those 2 points. So it would be the final position minus the initial position. So it's good to note here, too, that this can be positive or it can be negative. It depends on how you want to set up your axes. Traditionally, if you travel to the left, it's considered negative. If you travel to the right, it's considered positive. So think of like a graph, like an XY plot, right? If you're on the positive side of the x-axis, past the 0 point, everything counts up into the positives, and it counts down into the negatives as you go to the left of it. So for instance, this person, Stickman here, started at 5 meters and walked over to 3 meters. So this displacement would be negative because they ended at 3 and began at 5. So 3 minus 5 would give you a negative 2. So this little pictorial displacement would be negative 2 meters, would be the change in position or the displacement. Okay, so hopefully that makes okay sense that that's your displacement. The other vocab word, the term for position, changes in position, is distance. Okay, so this is the total length that is traveled. Okay, so if we go back to our example of the trail in the woods or something that you're hiking here, Most of the time, you're not going to go a straight line. You're not going to do a displacement. You're going to follow the trail wherever it goes. So you might end up walking a much greater distance, okay, and ends up coming back to wherever you ended up here on the trail. It's this total distance all added up, okay? And of course, distance, it can't be negative. You can't travel a negative distance. You either take a step left or you take a step right, but your distance is still one step. So it's only positive, okay? If you want to expand on this a little bit more too, let's say you do go hiking and you take this trail and you wander over to this area, and then eventually the trail ends up taking you back to where you started. At least you would hope, right? You get back to where you parked your car, or you started the trail, or wherever it is. But it gets you back to your location. You've traveled a great distance. You've traveled all over, and you've eventually ended up back to where you began. But your displacement at that point, you started here and you ended here. You started and ended at the same point. So your displacement at that time would be 0. Okay? So that's hopefully the difference between displacement and distance. We use both in physics. So it is good to know that, there are these two different terminologies depending on what the question is asking you for. Displacement and distance. Okay? More terms. Well, it takes some time in order to change your position, right? You don't instantaneously leave one spot and show up at another. It takes a little bit of time in order to get to another position. Okay, so depending on that amount of time, you'll have a speed, a velocity. Okay, we're going to start putting things into motion now. So, a velocity it's defined here by the equation that it's your change in position, your displacement, over the change in t, and t is going to stand for time, lowercase t for time. And this is only the time at which this displacement occurred. Okay, so it's a length. Okay, some position L, you've changed the length. It's some position, change of position length over a change in t, and that's time. That stands for seconds. So this would be a meters per second is how we end up getting a velocity. Now you can see it's a script v, lowercase v. That's how we denote velocity. You'll see that there's a little sub note of x next to it. That means we are traveling in the x direction, so we're using the x position for our displacement. And then you'll also see an average here. That's because this only takes into effect a couple of points, your beginning point and your end point. Okay, so it's not saying that you traveled the same velocity throughout your journey, but the average velocity that it took you, because you only look at the start and at the end points of your journey. Okay, so we see velocity often, if you watch sports, they might give you the speed of a race car or the speed of a baseball pitch, feet per second, miles per hour, kilometers per hour, whatever it is. Those are all speeds. Okay, it's a distance over time. Those are all speeds. Average velocities, I should say, rather than speed. I should say velocities rather than speed. Speed would be the next question, an average speed. So sometimes the average speed is the same thing as an average velocity. Other times it's not. It depends on the path that was taken. So this is the distance over time. Okay, so we use a lowercase d for distance. So remember, if we go back, that 1 is your displacement, 1 is your overall distance. So if these two are not the same, if you don't travel in straight lines and you do a weird curvy path, you will have a different speed versus a different velocity. Okay. So again, we call that a lowercase v. It's still velocity, it's still speed. No direction associated with it because distance does not matter. It's the terminology. It's not the equation so much, but the terminology that we will refer to this one as velocity, and we will refer to this one as speed. And speed, of course, just being distance over the change in time. So if you drive to wherever you live and you drive down to New York City, and then turn around and come back home, your average velocity would be 0 because you have returned to where you began, right? So your xf and your xi, your final and your initial, would be the same, and your overall velocity is 0. But now your average speed would not be 0. You have traveled 2 times the distance from you to New York, and however long it took you to do that journey, you would then have an average speed. Okay, so the speed that you see in your car on your speedometer, if you are driving, is of course a speed, not a velocity, because it doesn't know which direction you're heading. Okay, you don't know if you double back on yourself, and it doesn't pay attention to where you started or where you ended. And it's not important your average velocity. What's important when you're driving is your average speed. So we'll have these two terms. We have average velocity and average speed. Now, there is a way to get instantaneous velocity. Instead of averaging among 2 points, we can look at it in much, much closer detail to find an instantaneous velocity. So this would be a velocity at an exact time. And what we end up doing with it, for the algebra-based courses and for the calculus-based courses here, is we start minimizing our change in t. We start bringing our change in t closer and closer to 0. So instead of looking at the time maybe you were doing a 5K run, and if you look between minutes 2 and 3, you have a certain speed or a certain velocity in those 2 minutes, or in that minute. If you cut that in half, you look at your speed within a half a minute, or if you cut that in half, you look at your speed within 15 seconds, and you keep cutting it down smaller and smaller and smaller increments until finally your time is the change in time is very, very, very small and is approaching 0, and you will get your instantaneous speed at that very, very small amount of time. Now, for the algebra classes, this is all that we go over. Is just we tell you that it is the limit as t approaches 0. You will be using these 2 equations. We don't do limits, so you'll just be using these 2 equations. In the calculus-based version of this course, we do something where we do take that limit as t approaches 0. And as you know, you cannot divide by 0, so we have to have another metric in order for this to work, and that's calculus. This is what's known as a derivative. Okay, so if you are taking this course as the calculus-based version of this course, please check out my other video that I'm going to have on just doing derivatives and how they affect this. But know that this is the velocity in the x direction, no longer an average. When we do a derivative, this is the exact instantaneous velocity that we are looking for. Okay, so I will move on from that. But that's the 2 differences between the algebra and the calc-based. If you are in calc-based, please check out that other video. If you're not in the calc-based version, these 2 equations here are sufficient enough. Okay. We just have a few more terms. If you are already traveling at a velocity and you decide to change that velocity, let's say you're in your car and you're traveling at 10 miles per hour and somebody is honking at you to speed up, you will push your accelerator in your car and speed up to, say, 30 miles per hour. That is an acceleration. Okay. And accelerations work in very, very similar a similar manner. You'll see here that we have a lowercase a for acceleration. The x again, because we are only traveling in 1 dimension currently, so we have the x-axis. And again, it'll say average. So this is very close to the velocity equation. However, acceleration would be changing your velocity over a period of time. So instead of x, we have the velocity in the x direction. So we're looking at the change in your velocity from 10 miles per hour up to 30 miles per hour. And how long did it take you to make that change? That's the change in time. Okay? So if you do from 10 miles an hour up to 30 miles an hour, you would have 30 being your final, 10 being your initial, and you'd have 20 miles per hour up here. The amount of time it takes you to do that, I don't know, the power of your car. Let's say it takes you 2 seconds, right? So you'd have 20 divided by 2, you'd have an acceleration of 10 miles per hour squared. It's a little weird on the annotation, that's why we don't use We don't use miles per hour for our SI units. If we converted it all down into SI units, it would be meters per second squared. Okay, is the SI unit that we would use in this class, meters per second squared. But it's a change in velocity over that change in time. Again, we can do the same tricks using calculus. If we want an instantaneous acceleration, we would have a in the x, not an average, and we would take a limit as t approaches 0. So we would follow the exact same steps, and we would end up getting a change in v over a change in t at a very, very, very small amount of time, which would force us to take a derivative, and then our derivative here would be the derivative of velocity with respect to time. Also noting here that in calculus-based classes, you can also get to acceleration. Because you had to do a derivative on velocity, you could do a double derivative on position and end up with acceleration. You just end up doing it twice. So for algebra-based classes, the first equation up here is just fine, knowing that in order to get to a instantaneous, we would take a limit. This is all you'll need to know. For calculus-based classes, you will need to know how to take a derivative, how to go from one to the other. So for that, please check out the other video on derivatives. Okay, so these ones, now that we have a little bit of knowledge on this, we can do some combinations. We know that acceleration is the change in velocity over the change in time. Okay. If I were to start the clock at 0 every time, my initial time would be 0, right? So this would be a TF minus TI. If I start the clock whenever I choose to start the clock, my initial time is always 0. This makes the math a lot easier if you want to do that. Okay, so we always start the clock when the problem begins. So if I do that, this simplifies, okay, because t minus 0 is simply just t, however long it took in order to do this change in velocity. And then what we're going to do here is we're going to rearrange that equation. It's always a good exercise for math to go ahead and work these out and rearrange that equation. Okay, we can take t and multiply it by both sides. That'll get a times t over here. And what we're doing is we're trying to solve for this final velocity. Okay, so I'm just going to rewrite the equation to solve for the final velocity, which means I'll have to add the velocity initial over, and I should end up with this. If you're struggling a little bit with basic algebra, these are great. Okay, start with this equation here and end with this equation here. That's what I would like you to do. Okay, for the video, just to keep it nice and short, I went ahead and did it for you. These in the little yellowish, brownish boxes here. These are the equations that you need to know. These are the ones that will be provided for you. So these are the ones that I'm going to concentrate on. But a great mathematical exercise to go ahead and work through it. So our first equation that we get is if you're trying to solve for v final, actually if you're trying to solve for any of these, this is working. But this will give you a v final in one direction, x, is equal to whatever the initial velocity was in the x, plus whatever your acceleration is, times t, times time. Okay, so that's the first equation that we get. All right, then we take our velocity equation, which was xf minus xi divided by t is equal to vx average. Again, we're going to do some manipulation. I'm going to multiply the t to the other side, so you can see that we have vxt equal to xf minus xi. And in this one, what I want to do is I want to try and solve out for xf. Okay? So what I want to do here is solve for xf, meaning I need to add xi over to the other side. And then to find an average, I'm going to add up whatever the initial velocity was, the final velocity, and I'm going to divide it by 2, and that'll give me an average velocity. Now again, the math doesn't matter so much on how you want to go out of this, as long as you understand the final equation. So here our final position, our x final, is equal to our initial position, wherever we started, plus 1/2 of the two velocities added together. So this is an average velocity, times time, however long it took. Okay, third equation is another way of solving for xf. Okay, so in this equation, we take this v final that we have here in the second equation, and we use the first equation, v final, and we plug into here. Okay, so that's what we've done here is we've taken this equation from vxf and we've plugged it into vxf here. That should get you to this equation, which we're then going to rewrite in terms of xf. So this is the most popular one. We get xf is equal to xi, so final position equal to initial position, plus your initial velocity times time, plus 1/2 your acceleration in the x direction times time squared. Okay, so this one's a common one that you'll see in the kinematics. You'll use it quite a bit. And finally, your last equation, I will promise you I will make sense on why we are doing this so many times and that this is all these steps. In the last equation, we take one that we know, and we're going to substitute in time. We're going to rewrite the first equation for time, and we're going to make that substitution in for time. All right, so we take this first equation, we solve for t, and then I take t and I plug it in. I plug in t over here into this equation, okay? And we end up with this equation, which we're going to solve for vf again. Okay, so we've got two equations for xf, and we'll have two equations for vf, for position and for velocities. Always the final, because that's usually what you're solving out for. This one leaves it as a squared. So we have a vx final squared is equal to a vx initial squared plus 2 times the initial, or the acceleration, times the change in displacement, xf minus xi. All right, I promised a reason why we're doing all this. Okay, so the math steps there, they are important, especially if you're a physics major and you want to know how to work these problems. They're great little exercises to be able to manipulate equations, which will help you out later. But the reason for all of this, the reason for all of these adding in this equation to this equation to this equation to this equation is for elimination. Okay, you're going to be given lots of problems on kinematics. Every single one of those problems will have one of 5 things. You will have a displacement, okay, an xf and an xi. You'll have an initial velocity. You'll have a final velocity. You'll have an acceleration, or you'll have a time. So those 5 things show up in every single one of these equations, except one. Okay, so in each one, something is missing. You'll notice that we have 5 variables: displacement, 2 velocities, acceleration, and time. Something is missing from the first equation. Position. There's no position in the first equation. It's missing position. Okay, the second equation, if we look through that, okay, that one has position, it has the 2 velocities, and it has time, but it's missing acceleration. Okay, so this one does not have acceleration. The third one, position, velocity, acceleration, time, whoop, but we're missing the final velocity. We only have the initial. It's missing VF. And the last one has everything but time. There's no T. Okay, so this is why they're rewritten these 4 times, is that you have these 4 equations with 5 variables. Every single kinematic problem that you're ever going to get that you need to solve will give you 3 out of the 4 things that are in each of these equations. And the way I do it is I always make a list, and you can follow the way that I do it. You don't have to follow the way that I do it. I will make a list of those 5 variables, and I will put in what is given in the problem. There has to be 3 things that are given, and you always solve for the 4th. You look for what is not required. Okay? If the problem doesn't mention position, it doesn't care about position, you're not solving for position, you would pick the first equation because it has nothing to do with position. Likewise for all of the others. Okay? If you have a question that gives you 2 velocities and an acceleration and is asking for position, but it doesn't mention time, it doesn't ask for time, it has nothing to do with time, you would use the 4th equation because that one is missing time entirely. It doesn't matter. Okay, so hopefully that makes sense. We'll do some example problems and make sure that we go over that for you. There'll be lots of examples on this one, but first we got one more thing we want to cover, and that's free falling. So The kinematics are great because they work in either X or Y. Okay, you can use them horizontally when something is traveling across a plane, or you can use them vertically when something is traveling up or down. That is what we call the Y direction. There's something that's always a given in the Y direction. So it takes one of these things out of the equations, or not out of the equation, but it takes one of these things out of the question, that if something is falling in the Y direction, you can instantly assume that gravity is playing a part on it. The reason that it's falling is because gravity is pulling on it. Gravity is an acceleration. Okay, we always have gravity working for us. Near the Earth's surface, we can go ahead and estimate that gravity to be about 9.8 meters per second squared. That's always the acceleration that we're going to have of a free fall object near the Earth's surface. Okay, so we call that gravity or free fall. We can denote gravity with a little lowercase g, so you'll see that sometimes, that g is equal to 9.8. That's because that means we are near the Earth's surface. Something is falling, free falling in the y direction with an acceleration of 9.8. So that really helps out on the questions when not a lot of information is given, is that you know that gravity is taking effect only in the y direction and it has that specific acceleration. And again, we'll do lots and lots of examples of this as well. So stay tuned. I'm going to head over to a board and we'll go ahead and get started. All right, so here we are with chapter 2. So we got a bit more equations in chapter 2, so I just kind of want to go over some of these here right off that I have written up here in black at the top. Okay. The x we have learned is our position variable. Right now we're just in the x direction. We can change this to later directions like y or z, or if we do polar, we can do other things. But right now, x is considered our position. We need to know what we need for position. The triangle in front of it is the delta. That, of course, means change of. So this would be considered a displacement, change in x. And then we'll use whatever we end up with, the xf. Okay, so this stands for final. Normally we won't have final written. We'll just have a small lowercase f next to it to indicate it as the final. And that is, of course, minus your initial position, wherever your initial position was. And that's why it has an I for initial. Okay, so in the lecture we talked about displacement, distance, we've talked about velocity, we have an average velocity, and we have an average acceleration. Lots of new equations for us to deal with, and lots of new fun to have. Now, for this first example, I had to have something that moves. Okay, so being I have a board and I don't have a live animal to shove on there right now, we're going to have to go ahead and just use our imagination a little bit. Let's say I have a little race car here, so a little McLaren F1 car. And I want that car to start at position A, and then it's going to move. Okay, it's going to move to position B and C and D and E and F. And how it moves and the positions and the times at which it moves will make up these questions that we have. Okay, so this is the given part of the question, and then we're going to ask questions about it. So initially this car will start here at position A. Position A is at positive 30 meters. So I went ahead and I have written down the position A being 30 meters. And this is position A. This is the first position that we have. So we're going to start our clock at 0. Okay, so the car is sitting at position A at time equal to 0. 10 seconds later, we're going to look at its position again. Okay, so at 10 seconds, we'll look at its position, and we've seen that the car has gone from A over to B. Now, B is just above the 50, so we know it's at 52 according to our chart. Visually, yes, we can estimate that around a 52. 10 seconds later, we look at where the car is now. Okay, so the car has come forward up to point B. It has now been thrown in reverse, and it is backed up to point C. So you can see at 20 seconds, it is now at 38 meters. Okay, so we keep going. Position D, we are now 30 seconds in. Position D brings us to the 0 point. Okay, the 0 point on our x-axis is position D at 30 seconds. At 40 seconds, it is now at position E, okay, which is going to be a negative 37 because, again, the x-axis has a positive and a negative side. E being over here at negative 37, and it continues to back up all the way to position F. That is now 50 seconds that has passed, and its current position is negative 53 meters. Okay, so hopefully that makes okay sense. The car will go forward and then back up all the way at these different positions. Each position represents 10 seconds of time has passed. All right, so that's the build up to our questions. Now, our questions are going to be between the points A and F, so the beginning and the end. Calculate some things, right? And this is a 3-part question. One is going to have us calculate the displacement, and then it wants the average velocity, and then it's going to ask us for the speed, and speed is always the average speed. So we have 3 parts here that we have to work on. So let's take the first one, and then let's look at displacement. Okay, so how do we find displacement? So hopefully you're paying attention to the lecture notes. Displacement just means the total distance that was traveled. Okay, total distance that was traveled. Well, first it went from A and then it went to B. From point A to point B, it started at 30 meters and it went for 52 meters. So it gained 22 meters. Okay, it gained 22 meters here. Does that make sense? Okay, it went 22 meters. Then it decided to back up. Okay, and it backed up to C, backed up to D, backed up to E, backed up to F. We could figure out what the difference is on each one of these. Okay, so if it went from 52 down to 38, okay, it's a difference of 14. 38 to 0, that's a difference of 38. 0 to negative 37, it's 37 meters. And then the distance here from 37 to 53, what is that, 16? So this would be like the odometer on the car. How far did you travel? How many meters did you go? You went 22, you went 14, you went 38, you went 37, and you went 16. If we take and we add all of those numbers up, what do we get? Okay, we get the total displacement. So calculate the total displacement. You simply just add up the total distance that was traveled. Okay. Give you a second. Go ahead. Add up all that information. I believe we'll end up with 127 meters. 127 meters. And our units are correct, so we can go ahead and just box our answer for that one, 127 meters. Part 2, find the average velocity. Okay. Well, the average means we need to find out what the change in x is over the change in t. Okay, so let me do that one a little bit over here. We'll do some side work. The average, change in x, or change in t. What's the change in x? xf minus xi. What's the change in time? tf minus ti. Okay. What is xf? What's its final position? Well, the final position is when it's at f. That's when it ends. That's at negative 53. Okay, so I'm going to put a negative 53. And I want to know, well, where did it start? That's the xi. Where did it initially start? We're starting at A, which is at a position of 30. Then we work on the t's. When did we end the clock? We ended the clock at 50 seconds. Where did we start the clock? That's ti. Started the clock at 0 seconds. Okay. So what do we get here for our answer? Well, negative 53 minus an additional 30, going to give us a negative 83. 50 minus 0 gives us 50. Okay. So 83 divided by 50 should give us around negative 1.7. Okay, remember, velocities can be negative. That's fine. Average velocity, it went more in the backward direction than in the forward, so its final position was greater than its initial position, and that ended up, or more negative than its initial. That gives us a negative number. So we ended up with negative 1.7, and the units, of course, would be whatever our units are that we started with, and they have to be in SI units when we're done. So X needs to be in meters. Thankfully, it already was in this problem. T needs to be in seconds. It already was in this one. You can see them written out here. It was also given in the question written out. Okay, so what's our average velocity? Negative 1.7 meters per second. Box it. Okay. We've got our number, we've got our units, everything there looks okay. You can think back, does it make sense? Yeah, car went in the backwards direction. How about the speed? Is that also negative 1.7? No, speed is displacement over time, right? So remember, speed, even though we use the same beginning, speed is displacement over time. Okay. All right. The displacement, well, that was part A. No need to recalculate something when we already have it. It's 127. The time for the whole trip was still 50 seconds. Okay, still 50 seconds. 127 divided by 50 should give us around 2.5. Yeah. 2.5. And the units for speed are the same, meters per second. 127 meters, 50 seconds. Units are the same, slightly different equation to get there. All right, hopefully that one made okay sense. That was an example, a 3-part example: displacement, velocity, and speed. Okay. Now I'm going to clean this up, move on to the next problem. And so if you need to, pause here. Okay, let's look at a different kind of example. Here we have example 2. This one's just written out as a word problem. There is no visual to go with it. This says a particle moves its position according to a function. Okay, this function, x of t, which means position as a function of time, is equal to negative 4t plus 2t squared. Okay, so sometimes they're given as formulas, and that's position as a function of time. So every second that passes, it changes its position accordingly to that. So in this one, it gives a couple of different parts. What is the displacement between t equal to 0 and t equal to 1? And then also, what is the displacement between t equal to 1 and t equal to 3? So these are all times, right? T equal to 0 would be 0 seconds. T equal to 1 would be at 1 second. So what is the displacement between 0 and 1 seconds? Or what is the displacement between 1 second and 3 seconds? Okay. And then for the second part of this, what is the average velocity for those times? Okay, for the displacement from 0 to 1 and the displacement from 1 to 3. Okay, so we got a bit of work to do on this one. So first, what we want to do, okay, is figure out how we're going to figure out the displacement, right? What is the displacement between these two times? Well, we know what the displacement is. It's just the x final minus the x initial. Okay, that's the rule that we have for displacement, the equation. Okay, so if I'm going to do final minus initial, the first part here, let me do it over here on this side. I'll have the change in x is equal to whatever the final position is. Well, what's the final position? Well, the final position is a function of the final time. The final time would be t equal to 1. right? So if I do x of t equal to 1, I'm going to get negative 4 times 1. T is now 1. Okay. So I will get negative 4 times 1, okay, plus 2 times 1 squared. Okay, that's what I will get for my xi. Now I'm going to run out of room here if I don't change this up. So let me change this to xi. Okay, and what is that? Or sorry, xf. The final position. And what is that? Well, negative 4 times 1 will get me a negative 4. Plus 2 times 1 squared. 1 squared is just 1, so this is plus 2. So we get a negative 2 meters. Okay. Now meters was a given. If it doesn't state any other units that are given, you're going to assume everything's already in SI units for you. Okay. Most of the time it labels it in the question, but this one does not. So we have 2 meters, okay, for our XF. We need to do the same thing for XI. Now it starts at t equal to 0. So if I plug in t is equal to 0 there, I'll get x at 0 is equal to negative 4 times 0. Negative 4 times 0 is 0. Plus 2 times 0 squared. 0 squared is 0. Anything times 0 is 0. It's 0 meters. Okay. So what is the displacement between t0 and t equal to 1? Okay. The displacement here would be equal to xf minus xi. Xf is negative 2. Xi is 0. That means then the displacement, negative 2 minus 0 is negative 2 meters. Okay, we're going to do the same thing for the part B to this. Okay, what is the positions for T1 and T3? Okay, let's look at XF. Final position means I would have to use the final time for part B. The final time is 3, so let me plug in 3. So we're going to have negative 4 times 3. Plus, we'll have 2 times 3 squared. Okay. So what is that? Well, this XF, negative 4 times 3 is going to give me a negative 12. Plus 2 times 3 squared. You got to do squares first. So this will make 3 squared is 9. 9 times 2 is 18. Okay. Negative 12 plus 18 gives me a positive 6. That's my XF. I've done one part. Now I need my XI. XI is where it began. It began at 1 second. But hey, didn't I already figure this out up here at 1 second? Well, I sure did. At 1 second, it was negative 2 meters. Okay? So we can go ahead and reuse our answer from when the time is equal to 1, negative 2 meters. Now, if I plug in, I do the exact same thing. This will be XF. XF is now positive 6 minus the initial XI. XI is a negative 2. And we have 6 minus a negative 2. Minus a minus goes to a plus. So we'll have 6 plus 2, which gets us 8 meters. 8 meters for part B of question 1. Okay, hopefully that made okay sense. Working through it, we're going nice and slow, showing every single step. What is the average velocity for these times? Okay, that's a different equation. Average velocity depends on the displacement. Well, good thing we found out the displacement in part 1. Okay, we'll see this often as we do these multi-part problems. Okay, so for part A, we'll start here. With part A, we have V average, which is just going to be equal then to the change in X over the change in T. What was the change in X for part A? Change in X negative 2 meters. How about the change in time for part A? How much time has passed? 1 second. Okay, so the average velocity, negative 2 meters per second. Okay, for part B, we'll do the same thing. We have a V average. Change in x on that one is an 8, positive 8. And how much time has passed for part B? Well, this was time of 1 and time of 3. So 2 seconds have passed. 3 minus 1 gives us 2 seconds. 8 divided by 2 gives us 4. Okay, so there our answer for part B is 4 meters per second. After taking the calculus-based version of this course and you want to figure out what instantaneous is, I can have that up in another video. But for this one, let's move on to another question. Okay, we'll do another quick example here for acceleration before moving on to the kinematics. So this one here is also given as a function. Velocity of a particle changes as this function. So we have a velocity in the x direction equation. Okay, velocity as a function here, x. This is a function of t, but you do not see the t. Sometimes you'll see t in parentheses, sometimes you won't. Just giving you a variety of what to look for in these problems. But here we have v of x, and it's equal to 40 minus 5t squared. Okay, so that's our equation that we're dealing with, the function of time. Okay, it changes as a function of time. Here, we can calculate what the average acceleration is between two times, t equals 0 and t equal to 2. Okay, so we have an equation for average acceleration. It's up in the corner there, a average, and it works a lot like the velocity equation, except for instead of position, it uses velocity. Change in v over change in t, which means we need the final velocity minus the initial velocity. We need the final time minus the initial time. Okay. Now, we'll have to figure out what VF and VI are. So let's go to the side. Let's check out what VF is. Okay. So VF would be the final time. Here, the last time is 2 seconds. So let's plug in 2 for t. We'll have 40 minus 5 times 2 squared. Okay, what does that come to? Well, 40 stays the same. 2 squared becomes a 4, right? 2 squared becomes a 4. 4 times 5 gives us a 20. 40 minus 20 just leaves us with 20 meters per second. Okay, so our VF is 20. Now I figure out our VI. For VI, we plug in t is equal to 0. Okay, we plug in t is equal to 0, we're going to get 40 minus 0, which is going to just be 40. Okay, that's our VI. Let's plug in our VI. 20 minus 40. What is the time difference? TF minus TI. TF minus TI. 2 minus 0 gives us a resulting 2 seconds. What's 20 minus 40? That's a negative 20. And simplified down gives us a negative 10. Now the units. The velocities are in meters per second. But this is also over seconds. So it's meters per second, or meters per second squared. Okay, so here would be our answer onto this one, meters per second squared. Okay. All right, we're back with chapter 2. Couple more examples. We're going to have the kinematics. Lots of equations in this chapter, so lots to go over. So with the kinematics, I've written them up here in black. They're pretty much copied off of what we did in lecture, with just a couple of changes to make it easier to read on the board and to work out your problems. For one, I've omitted all of the lowercase subscript x's. We're only going to be dealing with the x direction for right now, or in y direction, we're going to be dealing with one at a time. So I'm going to leave all the x's off of the subscripts. The only other change I've made is that anywhere that there's a displacement, I've gone ahead and I've moved the minus or the x initial to the other side, which will give you a displacement. Xf minus xi is equal to delta x, and it just makes it a little more compact, a little more smaller to write onto the board. These are our 4 kinematic equations that we had talked about, and it's important to note that they all contain 4 out of the 5 variables that are interesting to us. The 5 variables we care about are displacement, initial velocity, final velocity, acceleration, and time. These 5 things are key to solving all of our problems for kinematics. And you'll notice that each one only contains 4 out of the 5. Each one is missing something. You'll notice in the first equation that there is no displacement. It is missing x. There is no x. Actually, it's missing delta x. Is probably I should put that. It's missing delta x. The next one, the second equation, does not have an a for acceleration. No acceleration in that one. Third equation is missing a final velocity. It has x, it has vi, it has t, it has a, but it has no final velocity. And the last equation over there has everything we need except for time. There's no time, which means each of these equations have 4 things, which means we only need 3 things in order to solve for a 4th thing. Let's do an example. It seems like a lot, but let's do an example. You'll see how they can help be much more simpler than they appear. All right, so in this example, we have a truck. The truck covers 40 meters in 8.5 seconds. So it's driving along, 40 meters has passed, 8.5 seconds is the time it took, while smoothly slowing down to a final speed of 2.8 meters per second. Okay, so it's slowing down, it's seeing something in the road or coming up to a red light or something. It's slowing down. Part A to the question, what is the initial speed of the truck? And part B says, what is the truck's acceleration? So a lot of students get confused with these ones easily, like, well, where do I begin? How do I even, I don't understand what's going on, okay? You should be able to picture this. It's just a vehicle traveling down the road, driving along, slowing down, putting on the brakes, coming up to a red light or coming up to a speed zone where they have to slow down. That's all this question is. Okay, it's just a truck slowing down, and it wants to know how fast was it initially going. Okay, hopefully we can picture that, right? Picture that. Now that we've pictured it, I could draw it if I wanted. We can go ahead now and extract some information out of it. Okay, so let's extract that. This truck covers 40 meters. Okay, it told me that on a purpose. So 40 meters must mean something. What's 40 meters? That's our displacement. It traveled 40 meters. That's the change in position. 40 meters. It did this in 8.5 seconds. 8.5 seconds is our time. Okay, 8.5 seconds is the time. While smoothly slowing down, that means it's our acceleration, but it didn't give us a number. Okay, so we can't put anything down for that. We know it was slowing down, but we can't put anything for a number. And that's the reason why it asks it in part B. Is, of course, it's not going to give it to you. It's going to ask you for that. So we know it's slowing down. And it slows down to a final speed of 2.8. Final speed. That's the final velocity. 2.8 meters per second. Okay? Now, we've got 3 bits of information. It's asking for a 4th bit of info. What is the initial speed of the truck? Initial speed would have to be initial velocity. So this is what the question is asking. What is the initial velocity? That's our 4th term. So what's the one thing we didn't care about? How do you solve this? You look at what is not asked of you. Okay? We don't know what the acceleration is. It was not given in the problem. It's the one thing that's missing from our table, right? It's not the question, and it wasn't given. There is no A in this problem. So you would grab the equation that has nothing to do with A. If A is something we don't care about, pick an equation that doesn't have it in it. Okay? There's only one equation up here that has A omitted. Okay? That's the equation. That's your clue. That's the equation you want to use because it doesn't deal with A. So let's grab that equation. We have delta x is equal to 1/2 vi plus vf over t, or times t, sorry. Vi plus vf times t. At this point, if you've drawn out your table like I have, now we just plug in what we know and we see if we can solve it. The change in x, take it right off your table. It's 40. Okay, equal to 1/2. What's the initial velocity? That's the thing we're trying to solve for. So let's leave it as vi because we don't know what it is yet. Okay. Then we'll have to add in, so we're going to do a plus, our vf. Vf is 2.8. And then this whole thing is multiplied by t. Okay? And t would be 8.5, given in the problem. Okay, so now you can see we've got all numbers with one variable that we need to solve for. So all we have to do now is just solve for that variable. And this is just algebra, right? It's just algebra at this point. What I like to do first is get rid of everything that's outside of these parentheses. You're kind of doing it in reverse order so that you have to do it correctly, right? You do it order of operation, you do it backwards to get back out of it again. So the first thing I see here is half of this. So if I were to multiply this whole side by 2, it would cancel the half, which means I have to multiply this side by 2. Okay, so if I multiply this side by 2, it cancels the half, but that means I'm going to have to multiply this side by 2. Okay, so I'm going to do this one out so that you see every step. Going forward on these, I'm going to expect you to know basic algebra in order to do these out. So what am I left with? Well, I've got a VI plus a VF. It still has to be in parentheses because I've got an 8.5 here. Okay, so 2 times 40 is 80. I've now done all my cancellations. What's next? Let's get rid of that 8.5. I'm going to divide this side by 8.5. Whoops. No longer VF. We know what that is. That's 2.8. There we go. Sorry about that one. Got a little mixed up there. All right, so we're going to divide this then by 8.5. All right, and that should give us 9.4. Again, some rounding in there. Now I can finally take off the parentheses because that's all that's left. Is 9.4 is equal to VI plus 2.8. Now we just minus 2.8 off of both sides. Okay. The plus 2.8 and minus 2.8 are going to cancel out, and we'll just be left with VI. Okay. Now that I've made it all the way down to the end, I'm just going to flip it around so that it gives us our answer here. VI is equal to 9.4 minus the 2.8. You want to plug that into your calculator, and you should get 6.6. 6.6, and it's a velocity. So 6.6 meters per second. Okay, that's our answer for part A. What's the speed, the initial speed of the truck? 6.6 meters per second. Does your answer make sense logically? Now that we have something, let's look back on it. We knew the truck was slowing down. It stated it in the problem, which means our initial speed should be greater than our final speed. And it is. And it has the correct units. Okay, that makes sense. It looks like it's good. It went from 6.6 down to 2.8. It stated it was slowing down. Good, good. That part is all right. Let's move on to part B. What is the truck's acceleration? Now it's asking for A. Well, we've got all four of the other things, so which equation should we use? Okay. If you've got 4 out of the 5, you've got lots of options. You can actually pick any of the other 3 equations and it will give you the correct answer. Any of them that you like. I always like to grab ones that are simple. It's just me. Equation 1 gets used a lot. Let's go ahead and use equation 1 because it has an A in it. It has everything else that we already have calculated. So we can go ahead and get our answer from that one nice and quickly. So I'm going to go over here. I'm going to write equation 1. Vf is equal to Vi plus At. Our Vf, we just grab it right off of our chart, 2.8. Our Vi, we just solve for it. We plug it in, 6.6. Plus, A is the thing we don't know, so I'm going to leave it as an A. T, we do know, given in the problem, 8.5. Okay. So now what do I have to do for this one? Well, this is a multiplication. This is an addition. I got to get that addition out of there. So I'm going to go ahead and minus the 6.6 from both sides. If I do that, this and this will go away. Okay. Now I'm going to end up with a negative number over there. It's a negative 3.8. Okay, negative 3.8 is equal to A times 8.5. Now, I got to get rid of the 8.5. How do I do that? I divide it by 8.5. One on top, one below. These are going to cancel. I also need to divide this side by 8.5. Now I'm at the final end. I can flip this around and I can say that A is now equal to, what is negative 3.8 divided by 8.5? If you plug into your calculator, you should get a negative 0.45. And acceleration would be meters per second squared. And there we've got our answer for part B of this. Now, it's a nice habit to get into. Once you've got a new bit of information, add it to your table. You might need it in other parts. Okay, as we get into more complex questions, this might just be the first parts of a question. And again, of course, your final thing, does the answer make sense? Why is it negative? It's negative because they're slowing down. The acceleration, of course, would be negative. It means it's accelerating in the opposite direction. The car is slowing down. If it keeps slowing down and it keeps that acceleration, eventually it'll come to a stop and it'll start backing up. So the equation, the answer, everything there should make sense. That's your first look into kinematics. Okay, hopefully that was all right. Okay, let's do another example on kinematics. So this is example 5. So this time we have a jet that's going to land on an aircraft carrier. So this is kind of fun how these do this. There's a big cable that lays across the top of the boat. When the jet comes in, the cable snags onto it and it acts like a big spring and it slows it down. Anyway, a jet lands on an aircraft carrier at a speed of 63 meters per second. What is the jet's acceleration if it stops 2 seconds after its first contact? Okay. And then part B, what is the jet's final position if its first contact is xi equals 0 meters? Okay. So let's see, it would be, let's say we've got an aircraft carrier in the water, and we've got a plane here, a jet coming in to land on that aircraft carrier. All right, so when it comes down, okay, and it makes first contact, this is what we're considering xi to be 0 meters. And then at some point it's going to stop. So at some point it will be over here at some XF, we don't know. Okay, but it has now stopped on the aircraft carrier. And let's see, we know here that the speed at which it was coming in. Let's add all that to our chart over there. Okay, so that's a picture of what's going on. Okay, and what's kind of happening on it. Plane's going to come in and land. Everything is in the X direction because the ship, we can say, is floating on the water and it's flat. Nice calm water, I guess. So it says a jet lands on an aircraft carrier at a speed of 63 meters per second. So what is that telling us? Well, that's the speed at which it landed, right? That's the initial speed at which it was coming in to land. So on that one, our initial speed, 63 meters per second. Boy, that question didn't give us a lot. Let's keep going. What is the jet's acceleration? Okay, so that's the question. What is the acceleration? So what is A in this case? If it stops 2 seconds, all right, 2 seconds would be our time after first contact. Okay, so first contact, xi is equal to 0, but it doesn't tell me how long the aircraft carrier is. So I can't put anything for the change in x because it only tells me that xi is 0. And especially since xi is given in part B, I shouldn't need part B to solve part A. So I can't put anything for the change in x, which means I'm missing final velocity. And it comes from the keywords in the questions, right? You want to read these questions thoroughly, that this thing's going to come to a stop. So what's its final velocity if it comes to a stop? 0. It's going to be 0 meters per second if it stops. That's the final speed, is 0. All right, so that helped out, saved us. Now we have 3 bits of information. We're looking for A. What's the thing that we don't care about? X. All right, so we don't care about x, which tells me I need to use the first equation. So I'm going to write out VF is equal to VI plus A times T and see if this works for me. VF I know to be 0. VI I know to be 63. Plus, I don't know what A is. I'm going to leave it as A, but I do know T is equal to 2 seconds. Okay. Now, how am I going to get A by itself? Well, first off, let me minus that 63 to the other side. So I'm going to have 0 minus 63, so negative 63 is equal to A times 2. How do I get rid of the A times 2? I'm going to divide by 2 on both sides. This will get rid of the 2. Okay? So now I'll have A, so again, I will flip the equation around so it solves out nice and pretty like. I have A is equal to this negative 63 divided by 2. What's 63 divided by 2? Well, we'll get a negative 31.5. And it's an acceleration, so that's meters per second squared. All right, so there's our acceleration. I'm going to add it to our table. Go back and look. Does that make sense? Remember, we just looked at a truck that was slowing down, coming from like to a stop sign or into a speed zone, and a truck was slowing down. Do you remember its acceleration? It definitely wasn't negative 31. That's a big number, negative 31. Does that work for this equation though? This problem? Well, this is a jet landing on a little boat, so I would expect the number to be greater, right? It's slowing down. It has to slow down a whole lot faster than a truck on a highway. So negative 31.2. Sure, I'm going to go ahead and say that that's roughly a correct answer. It's in the correct range. You might ask, well, how would you know? I mean, what is something that's out of range? Okay. If we looked at acceleration, you had negative 10,000 meters per second squared. That's an insanely high number compared to the boat or compared to the truck, right? The more problems you do, the greater your knowledge is going to grow on whether these make sense or not. Okay, so something that's astronomically big or positive would be something that would be incorrect, right? Because we know that the plane is slowing down, it's coming to a stop. We would expect the acceleration to be negative. It's the opposite if the problem were something speeding up. We would expect the acceleration to be positive in that case. Okay, so little things like that to keep in mind as we go along. That seems okay, right? Our acceleration is negative. It's 31.5. Okay, we'll go with that for the acceleration. Part B to it. What is the final position if its first contact is xi? Okay, so what it's looking for here now is xf, right? It wants the final position. What is xf? I don't have an xf here, but I can get xf from delta x. Right? So if I solve for delta x, I can figure out what the final position was. So I need to do a two-parter. First off, let's find delta x. I have every other bit of information, so I can go through and I can pick any one that I would like in order for that, in order for me to find out what that position is, or displacement. So I'm going to grab number 2. Okay, I'm going to grab number 2. And number 2 here is going to tell me that I have a change in x equal to 1/2 vi plus vf times t. Okay. Change in x is what I'm looking for, so I'm just going to leave that one alone as change in x. I'm going to add in my 1/2. My initial velocity is 63. My final velocity is 0. And my time is 2 seconds. So how about that? That was quick, huh? Delta x is what I'm solving for, so I don't need to move anything over there. I have a 1/2 times a 2. Okay, 1/2 times 2 is going to cancel each other out. And I'm going to be left with a 63 plus 0. I'm going to end up with a delta x of 63. All right, this is equal to xf minus xi from the previous videos. Right, what's xi? They've set xi equal to 0. Okay, so if I put xf equal to, or minus 0, it's just xf. So what is xf? It's just 63. Okay, it's just 63 meters. So this is our answer for part B. And it would make sense then that the length of the ship is around 63 meters. It's nothing giant. It isn't the size of a planet, and it isn't the size of a housefly. 63 meters, remember each meter is almost 3 feet. 63 meters is a longer distance for it. So sure, makes sense. Okay. Just for clarity, just for a point on this, we can go ahead and pick any of these equations that we wanted. I just happened to pick number 2. Okay. We can pick any of the other ones as well, and we'll end up with the exact same answer. So let's say I pick the third equation, right? So this is just extra. You don't need to do any of this. We're just going to go ahead and do the third equation. So on the third one, I would have a change in x is equal to vi times t plus 1/2 at squared. Okay. If I went through, again, I'm just solving for a change in x. My initial velocity, you'll see, is 63. The time is 2 seconds. Plus, I'm going to have 1/2. My acceleration, negative 31.5 times my t squared. Okay, so it's a bit more than this one. Not quite as easy. Just saying you can choose a different path and you can still get the same results. Okay. So if we go through this, I'll have 63 times 2. So that's 126. Okay, 1/2 multiplied by 4 is going to give me a 2 times negative 31.5. Okay, are we seeing it now? It's starting to come in, maybe, hopefully. All right, 126 plus 2 times negative 31.5 gives me a 63. A negative 63. So we'll be plussing a minus 63. And 63 times 2 gave me the 126. So it's really 126 minus 63 gives me 63 meters. So it all works out in the end because all of these equations, remember, are all based off each other. So it doesn't matter which one you use when you have all four, as long as it has the variable in it that you're trying to solve for. So you can do one that is much more, has more steps. You can do one that has much less steps. You'll still get the same answers, so their guessing is not wrong. Okay, pick which one you would like. The more you do, the more you'll find out that some of these are easier than others. All right, so there's your example number 5 for kinematics. We'll move on to the next one. Okay, so let's try another example here. This is example 6. This will be our last one. In this example, we have a word problem. It states here that we have a stone that is thrown from the top of a building at an initial velocity of 20 meters per second. The stone is thrown straight up. Okay, so the building is 50 meters from the ground. Okay, so what does that entail? Well, being it didn't give us a picture, we can go ahead and kind of try to draw one. I have a building here. It tells us that the building is 50 meters tall. And let's see, I guess a person would be a pretty small person up on top of a 50-story building. And they've got a rock. And it says they throw the rock with an initial velocity, but the stone is thrown straight up. So they must throw the stone straight up into the air. Okay. From the top of the building. Okay, so that makes okay sense. Well, what happens when you throw stones up in the air, right? Eventually, it's going to hit a point where it's going to turn around and it will start falling back down. Okay, so we can kind of picture what's going on here. So this is our 50-meter tall building. We can give it some windows if we like. We can give it a little kitty looking outside. Okay. And we are throwing rocks from the top of the building. Not the best thing to be doing. I want to walk through and see if I can grab everything I can out of here. It doesn't look like a whole lot of numbers are given, but hopefully something will make sense. So, being thrown from the top of the building has an initial velocity of 20 meters per second. Okay, so 20 meters per second, that's going to be the initial velocity. It gave it right there. Right in the problem, so we know we can put down 20 meters per second there. Being the stone is thrown straight up, that means that all of my x's for this problem can get turned into y's. Okay, so I'm either in the x direction when I look at the kinematics, or kinematics can also be used in the y direction, but they have to be used in one or the other. You cannot mix and match x's and y's in the kinematics. They need to be one or the other. It's for one-dimensional motion. That's the whole point of the chapter, right? Okay, so I can make those changes in the y direction, being that it's thrown straight up. Okay, so that's why that little bit is in there telling me this is a free fall object. The building is 50 meters from the ground. Okay, so if I could plug that into my delta y, but that's not right. The delta y is the change in y. Well, what's moving in this problem? Is the building moving? No, the building's staying stationary. It's 50 meters high. The stone is the thing that's moving. Okay, so what's the change in y? I don't know. I don't know what the change in y is because it hasn't been told in the problem. It gave me an initial velocity and it says it's thrown straight up, but it doesn't tell me how far it goes. Okay, so I have to go into my problems now. How much time passes? Okay, how much time? So that's what we're looking for. How much time passes before the stone changes direction? Okay, so what does it mean when it changes direction? I throw the stone straight up into the air. The stone then changes direction right here. There's a change in direction. How much time has passed when the stone changes direction? That doesn't give me any numbers. How am I going to solve this one, right? So, a couple things we need to think about on this one, okay, that are not explicitly given in the problem, but you need to put together, okay? You need to self-think through this problem and put these things in order. So, something specific happens when it changes direction. What happens there? Well, imagine this is the stone. Stone gets thrown up in the air, it slows down, it comes to a stop, and then starts coming back down again, right? If this is positive direction, it stops and it starts to travel down in a negative direction. So there has to be a point when it changes direction that it momentarily stops and then it goes the other way, which means at that instant, when it changes direction, the velocity is zero. Okay, so it's starting off at 20 meters per second, and when it changes direction, it goes to 0 meters per second. But that's still only two things. I need one more thing in here in order for me to be able to solve anything. I need 3 out of the 4 things. And I only have 2. I need a third, and then I can solve for the fourth. So being that this is a y direction problem, this states a free fall object could be occurring. The stone is a free falling object, which means it will have some acceleration due to gravity. Okay, gravity is what is going to pull that stone downward, and it'll pull it downward with a magnitude of 9.8 meters per second squared. So the negative dictates the direction. Okay, everything gets pulled down according to gravity, so the downward pull will give it a downward acceleration in the negative direction. Cool, so now here's my 3 things. I'm looking for time. I don't care about delta y, which means I'm back at that first equation again. Okay, so let me put up here VF is equal to VI plus A times T. Okay. RVF, good to know that's a 0. Our initial velocity, that's a 20. Okay. Plus our acceleration, that's a negative 9.8. And T is the variable that we're trying to solve for. Okay, so again, just for clarity, I want to get rid of the addition here on this side first. So I'm going to minus 20 to the other side, right? So if I'm minus 20 from here, we'll have a cancellation. 0 minus 20 is going to give me minus 20. And then the 9.8, negative 9.8 times t just follows suit. Okay, so hopefully these steps are now making okay sense. We can now go ahead and divide by negative 9.8, divide this side by negative 9.8, and we would punch it into our calculator to get a t. Okay. Now this is very, very close to 2 seconds. It's actually, we're just going to round it on up to 2 seconds. That's our change in time. That's the time that occurred. So I can add that in here. Okay, I can add that into our table. Now, does that make okay sense? 2 seconds, stone goes up. Does it take about 2 seconds for that to turn around? 1,000, 2 1,000. Okay, that makes okay sense. It's not anything like a minute, or it's not too fast. So 2 seconds, I think that answer makes logical sense. It seems okay. Okay. Now let's look at the next part. Okay, hopefully that made okay sense. We'll go ahead and move on with part B. What is the stone's displacement at that height? Now we want the delta y, right? We want to figure out what the delta y is. How much did the stone change its displacement? So for that one, I can go ahead and I can pick any of the other ones that I would like, as long as they have the delta y in them. So I'll go through and let's just grab, you know what, this one is nice and easy last time. I did that as an extra one just to make sure it was there. We can already, let's just go ahead and try out the fourth one, because we haven't tried that one yet, right? So let's go with the fourth. I'm going to get down here. I will have VF squared is equal to VI squared plus 2 times A times the change in Y, because we are in the Y direction. My final velocity, nice and easy, 0. 0 squared is still 0. My initial velocity was 20. 20 squared plus 2 times the acceleration, that's a negative 9.8, times the change in y. Okay? And again, you can pick any of them that you'd like. If you'd like, pick the second equation. You could probably do it faster than me. On to this one, using the fourth equation, it'll give us the same answer. 0 squared is still 0. Okay. 20 squared is 400. So I'm going to go ahead and minusing that 400 to the other side. Okay. That'll give you that. Again, if you're getting confused on the steps, this is 0. This is 400. I need to get rid of this addition first. Okay. So I'm going to get that over to the other side over here by minusing it. And 20 squared is, of course, 400. Being it was positive, it goes negative when it goes to the other side. 2 times the negative 9.8, we can go ahead and get rid of that as well by just dividing by it. What is 2 times 9.8? 19.6. Okay. If we divide by negative 19.6, you'll see because it gets negative because there's a negative in here. Okay, we'll end up with delta y is equal to whatever, negative 400 divided by negative 19.6. Plug that into your calculators. What do we get? Negative 400 divided by negative 19.6 gets us 20.4 meters. That's our displacement. Okay. Remember, it has nothing to do with the height of the building. Our displacement is the initial and the final points. Final minus initial. Where's the final? The final is above the initial, so our delta y is positive, 20.4 meters. So hopefully that makes okay sense. The building is 50 meters, so almost half, a little less than half of the height of the building. That's a good arm. All right, somebody's really throwing a rock up there. It must not be too heavy of a rock. All right, so we can go ahead. We can add that up here if we would like. Okay, 20.4 meters. And there I've given you a demo of each of the kinematics. And of course, you're going to use those in all of your homeworks as well. Leading up, you're going to use them more and more as we go throughout the course. So I think that's a good intro on it. You'll follow the same steps for all of these kinematic problems. Okay. Hopefully that'll work out for you. And I'll see you on chapter 3. Again, email me if you have any questions.